Okay, thanks so much for the introduction, and it's great to be here. As Jason said, I would love this to be interactive. I'm going to tell you about some recent work, and particularly going to cover a model we've been developing, and I think it's a little bit technical at times, so if it doesn't make sense to you, please just stop me, ask questions at any point, just interrupt. I'd love that. So today I want to tell you a little bit about the work we've been doing in terms of how you learn multiple things over your lifetime. And so we think about the problem of, from the continuous stream of sensorimotor experience, how you might build up different motor memories for different tasks or different environments. And so to illustrate this, with a very British example of making a cup of tea, there are different discrete elements making a cup of tea. The hand is free in space at some point. At other points, the hand is interacting with a kettle, and then is free again, and then interacts with the teapot, and then goes back to the kettle, and so on. So we, as humans can say, oh, well, let's label these with different contexts, for example. So these green contexts, for example, is when the hand is free in space, and that clearly has different dynamics than the cyan ones where you're in contact with the kettle. But these sort of contexts change discretely. So, as we change from one context to another, the dynamics of what we have to interact with change. But within each of these contexts, we can have different states. For example, as you pour from the kettle, the weight of the kettle will change. Or as you swish around the teapot to warm it up, the dynamics change. And so the fundamental question we want to think about is, how does the brain learn the multiple contexts and multiple states we experience through everyday life? And so I'm going to start by going over the way we address this experimentally in the lab and give you some background of the rules for motor memories and sensorimotor learning. And then I'm going to dedicate the majority of the talk to a new model we've developed, the COIN model, contextual inference model, which really talks about the problem of learning a motor repertoire in terms of trying to understand how you create memories, how you express memories, and how you update them. And I'll talk about some experimental tests of the model on new and existing data. And if there's time, I'll talk a little bit about cognitive aspects of motor learning. So we go to a lot of effort in the lab to make sure that when we look at motor learning, we give people very novel experiences. We don't want to bring people into the lab and give them objects to interact with, which they've seen outside the lab, because then we're looking at recall rather than de novo learning. And so to do that, we build robotic devices. So this is a typical robotic device. This is a planar device. So the subject can hold on to the end of it and move it on the plane. And this is a side view. And we can overlay visual feedback into the plane of the movement. So we can have a monitor here face down, a mirror here, so they see images in the plane of the movement. And we can ask them, for example, to make pointing movements to a series of targets. The robot can both track the movement, but also generate forces at the hand. So we can generate forces at high update rates at the hand in relation to what the participant's doing. So for example, we can have the motors off. So we can ask them to make a movement with the motors off. And I'm going to use some nomenclature throughout. That's P0, meaning nothing's on. It's a null field, we would call it. But then we can do something which is typically used in the field. We can apply forces at the hand, Fx and Fy in the X and Y direction, which are this gain times this matrix times the velocity of the hand, the X and Y direction. And so if I plot out what this force would do to the hand, this is a vector field you would get. So this is the X velocity and the Y velocity. And these blue arrows show you the force you would experience at your hand. So if you don't move, you get no force. The faster you move, the bigger the force. And the force direction is always at right angles to your direction of movement. So if you move to the right, the robot's going to push you up. If you move up, it's going to push you to the left. So we call this a velocity-dependent or viscous curl field. It's an unusual field and one you won't have experienced outside the lab. So it's a nice one to use because we can then look at how you learn this force field. So if we apply this force field on a movement like this, little red arrows show you the forces you'll experience and you'll get perturbed. But if you did that for half an hour, your movements would become straight again. And in fact, you would perceive that the force field has been turned off. You sort of internalize it. So we're going to call that a P plus field. It's a field which acts in one direction. In this case, the plus means it acts to the left of you. And of course, we can change this sign of this gain here, K, and apply the force field in the other direction, P minus. Okay, so in general, P plus and P minus just opposing force field. One pushes you to the left, one pushes you to the right. We actually, in all our experiments, counterbalance which one is P plus and P minus. And then to assess learning, there are various ways. We can assess learning by looking at how much you deviate, for example, from a straight line path. But we don't tend to do that because it's hard to quantify that in terms of how much you've adapted to the force field we're producing on you. And so what we tend to do is you use what are called channel trials. On these trials, which only happen occasionally, we apply a one-dimensional stiff spring with the robot. So we constrain the movement to a straight line to the target by a stiff spring. So from the participants' point of view, they think they were doing an amazing job. They produce a lovely straight line movement. But we can measure the force the subject produces into the walls of the channel as a measure of what they anticipate the compensation they're going to make is. So for example, here is the force which would ideally compensate for this force field as a function of time. And we can measure the force the subject really produces as blue line here. And in this case, they haven't learned very much. Maybe later on in learning, they produce this blue force. And so we can regress effectively the green against the blue to get a percentage compensation, a number between 0 and 1 or 0 and 100%, the extent to which they've compensated for the force field. So we like to use these channel trials for two reasons. They give us a percent adaptation and it's independent of co-contraction. You can compensate for these force fields by stiffening up the limb, where stiffening up won't help you compensate in a channel trial. Okay, so just to reiterate, P0 is a null trial, P plus and P minus are two different directions, and we use these channel trials to assess learning. So here's a typical, very simple experiment. Subjects come in, they do a bunch of P0s, and this actually is plotting the deviation from the straight line. So they make straight movements. We apply P plus, they're perturbed. Over the course of an hour, they get better and better. We turn the force field off and they show after effects in the other direction. Again, we don't tend to look at this data. We tend to look instead at the channel trials, which interspersed maybe 1 every 10 trials. And this shows you the channel trials. They started with no adaptation, and over the course of the experiment, they adapt to about 75% in this case of total adaptation. Okay. So what we've been interested in recently is what allows you to learn two different memories at the same time. And so if there are two different memories we're going to look at P plus and P minus. So for example, we can give subjects a P plus trial, one where the force field acts to the right. And in fact, we're going to turn on this little green light here to alert them that it's going to be a P plus trial. And on other trials, we'll give them the P minus, the opposite force field, and turn on this light in a different place. Okay, and we interleave these trials randomly. So although I'm showing them in different points on the screen here, they're actually overlaid at the same point in space. On every trial, we randomly select P plus or P minus, and before the movement show this green light to the left or the right. So cognitively, you could imagine that they could learn when this is on, I need to compensate for this field, and when this one's on, compensate for this field. And if we then test learning by occasionally using our channel trials, what we see over the course of an hour or so is fundamentally no learning. They show absolutely no adaptation to these force fields, and so the adaptation meanders around 5% at most. Okay, so it suggests that it's impossible to learn these two force fields if they're interspersed randomly, even when there's a sort of static visual cue to alert them to the force field. Okay, and actually this has been known for a long time, that it's very hard to get subjects to learn two different memories at the same time and express them on different trials. But we can change the paradigm just a little bit. So rather than make this just a visual cue, which is informative somehow cognitively in terms of the force field, we now ask the participants to start their movement from either the left or the right cue. They're going to move in without any force field and then go through the force field. And the direction they move in from, if they come in from the left, they're going to get the P plus field. If they move in from the right, they're going to get the P minus field. So the direction of the lead in is predictive of the field they're going to get. And in different groups of subjects, we're going to make them wait at this start point for different amounts of time. So for example, if we have a group who has to wait 1 second, so they come in here, they wait a second, and then they go through the force field, or they come from here, stop here for a second and go through this force field, we see no learning, just like the static cue. But if we only make them wait half a second at this point, we begin to see a little bit of learning. So now at this point, we're getting about 30% learning. If they only have to wait 150 milliseconds, we get more learning. And if we really say you only have to pause for 50 milliseconds, which is basically almost no stopping at all, we see substantial learning. So it suggests that if what you've done with your limb in the half a second or so before you go through the force field is different, then you can begin to separate out the motor memory. So it suggests to us that the history of your movements is informative to allow you to separate out motor memories. And if the history of what you do is different in the last 500 milliseconds, that allows you to associate this force with one memory and this with another. If it's more than 500 milliseconds ago, like the 1 second, it's no longer useful for separating out those memories. And so this was sort of surprising to us, but also made us think a little bit about if the past is important to separate out memories, could the future also be important? And so we did a very simple experiment in which we said, if the future is different, would that allow you to learn separate motor memories? And so we have a control group, very similar to our leading control group. Now, there's a target here which is irrelevant to the participant, except it's informative of what force field they're going to get. So this is a no follow through group. They just make a movement and stop, but this target will tell them whether the force field is left or right. And again, we get no learning at all under that situation. But in another group, we tell them they have to move through the force field and then follow through either to the left or the right. And now the direction of the follow through is informative of the force field they're going to get. And when we allow them to follow through, and remember the force field's only on the first part, not on the second part, we see substantial learning. So it suggests not only is the past helpful to separate out motor memories, but you can use what you can do in the future. And if what you can do in the future is different, it allows you to somehow separate out these motor memories. And this was sort of interesting to us because, you know, in sports science, people always tell you following through is really important in sport. You know, even though after you've made contact with the ball or released the ball, whatever you do after that can't affect the flight of the ball. So why should following through ever be important in sports? And one reason is that if what I told you is true, that different follow-throughs activate different memories, then if you were to make a consistent follow-through after a skill, for example, learning just a single force field P+, you would be activating a single memory and all the learning for this P+ would go in one memory. On the other hand, if you were to make different follow-throughs on each trial, so always go through the P+, make a different follow-through, you might be spreading your learning over multiple memories. Okay, in the same way as when we had different follow-throughs, you could associate them with different memories. So we ran a very simple experiment, one in which one group of subjects go through P+ and do a consistent follow-through. Now, we're just learning one thing here. It's not opposing fields, just one force field. And another group, again, went through the P+, but then made a different follow-through on each trial. And what we found is this group with a consistent follow-through learned significantly faster than the variable follow-through. So we suggest that one reason, probably one reason only, that you might want to make a follow-through and make a consistent follow-through is to ensure that any learning of the movement before the follow-through goes into a single memory effect and gets consolidated. There are many other reasons you might want to follow through I won't get into, but this could be just one reason. So this is just a replication of our two groups. Here's the no follow-through group again and a follow-through group who learn. But we were interested to try and work out what it was about a follow-through which allows to separate out memories. So it could be that what's critical is that you execute the follow-through. So we have one group who get to execute the follow-through, but never plan it. So they start off their movement without a follow-through target, either in the P+ or the P- force field. And halfway through the movement, we turn on the follow-through target, and they follow through to the left for P+ or the right for P-. So they could learn to associate this target with the P+ field and this target with the P- field. And the way we assess that is on occasional channel trials, we put on the follow-through target from the start of the movement. So they make the follow-through, but on these trials, there's nothing to learn. So we're assessing learning when they can have information about the follow-through from before, but on the execution-only trials, they don't get to plan the follow-through. And when we assess learning on these trials, we can see they learn absolutely nothing. So just executing a follow-through after the field isn't enough to let you separate out the learning. But we have another group who get to plan the follow-through, but never ever make the follow-through. So they see the target from the beginning of the movement, the follow-through target. They start the movement through the appropriate force field, and halfway through the movement, we turn off the follow-through target, and they have to abort the movement at this endpoint. So they never get to make the follow-through, but they can plan it. And the way we encourage them to plan it is we have many of these trials where effectively they get to make the follow-through, but there's nothing to learn because they're in a channel. So that encourages them to plan for the follow-through. And so when we assess learning on these trials, what we find is that the planning only group showed just as much learning as a full follow-through, which suggests to us what's critical about follow-through is nothing to do with the execution of the movement. It's got to do with you putting your brain effectively in a different state by planning the follow-through. So it suggests to us that the recent past, and I don't know the right word, the recent future, determines the current motor memory. If they differ, then that allows you to effectively separate out motor memories. And that planning is more important from execution. So what we're really thinking is that what's critical to allow you to learn separate memories is to have to a different neural state. The physical state doesn't really matter. What matters is the different neural state. And by planning to make a follow-through movement, you effectively put your brain in a different neural state for the initial part of the movement, which lets you separate out those memories.
Daniel, it's interesting that in the previous slide, when you have the variable follow-throughs, it only affects dynamics, but not the total amount of adaptation.
That's right. That's right. So I think effectively you can always top up the multiple memories to get you to the same level in the end. That's just for learning a very, I remember this is rather different, just for learning a very simple single force field. And in fact, we've done modeling of that, which suggests that it is the fact that, you know, they decay away between, but as long as you keep topping them up, you get to the same level. Yeah. Yeah. So what I've talked up to now is really about using sort of contextual cues to learn, but not about using sensory cues. And I don't want you to go away thinking the only way you can learn sort of multiple memories is by, you know, lead in and follow through. We're very interested also in tool use. And, you know, if you look at different species, for example, different birds, each have got amazing tools. They've each dedicated to a single tool, which they've learned. But we as humans are amazing tool users, so we can use all the same tools which we've acquired from, you know, bird-like tools and more. And one thing which is interesting to us is when you act on an object, for example, such as a cup, do you learn it in terms of motor learning as a physicist would learn it, you know, F equals ma, learning the physics in terms of the properties? Or do you learn it in a much more sort of goal-directed manner? So, for example, you know, you do different things with a cup. So when you drink from a cup, what's critical is the interaction between the lip of the cup and the compliance of your own lip. And that has a particular sort of dynamics, which is rather different from when you're putting a cup down the table. What's critical is the frictional properties between the hard surface and the surface of the cup. So you can imagine when you do different things with a cup, there are different points you want to control, and they have different dynamics associated with them. And so we were interested to ask the question is whether when you control different points in an object, you can effectively associate them with different dynamics. So we had a very simple experiment. This is showing you what the subject saw. So the subject can see their hand holding the robotic handle, and then we overlay, using a semi-silvered mirror, an object into the plane of movement. In this case, the object is this rectangle. And you can see that there are different points on the rectangle, which we're going to ask the subject to control, and we can put targets into the plane. And so we can have a very simple experiment, very similar to what we've done before, where we ask subjects to move the central control point to a target, and either we put on a P+ force field, or in other trials, a P- force field. And again, there's this irrelevant target, which is this one over here, which tells you the force field they're going to get. But for this group of subjects, it's irrelevant to their task, so they can ignore it. And what we find is in this group, there's no learning at all. But we can have another group of subjects who get to make the same movements in the same force field. But now we tell them, if there's a target on the left, we want you to move the left control point to that target. There's a target on the right, we want you to move the right control point to the target. Now, critically, both these movements are just the same as this group's movements. Basically, it's a straight ahead movement for both these. So they're making exactly the same movements, experiencing exactly the same force fields. The only difference is what they're being asked to control, the left or the right control point. And when we do this experiment, what we find is they show remarkable learning. They can learn extremely well. So they can learn to associate a P+ with controlling this point and a P- with controlling that point. It's got nothing to do with eye movements. We can do the experiment with fixation or with free gaze. It doesn't make any difference to the learning. So it suggests to us that effectively the way we learn about the way we control tools is in sort of a control point dependent manner. We can learn for different points, different dynamics. So control points for objects can be associated with different dynamics for the same movement. And I'm going to link that in the second half of the talk to the idea of sensory cues. Effectively, the control point is a very strong cue to the context of what force field you're going to deal with. Now, I'm going to move on to the next slide to our new model. Any questions on the data before I do that? Okay.
Sorry, I have a question.
Yes.
So I wonder in these types of experiments, including this one and the first one you've shown, so what comes into my mind is basketball players standing on the foul line and shooting. And as you know, they have this full, I would say, ceremony, both before and after. And some critical points of this ceremony seem not to relate to motor or visual things at all. For example, the way they breathe or the way they move muscles that are totally unrelated to the muscles shooting the ball and performing the motor action. So I'm wondering, how can you, are there experiments in which you can tease apart these non-motor components?
So we haven't done that. I mean, it's certainly the case that you can actually do things with other parts of your body. So I've talked about, follow in. It turns out that if you move your other hand and your other hand is doing something different, then you can learn two different force fields. So for example, if I'm learning a force field with my right hand, if I move my left hand back for one force and forward for the other, it allows me to separate out those memories. So other parts of your body somehow act as context. Now, my belief is that in the basketball, probably it becomes what they call superstitious type movements. So when you take mice, for example, and ask them to do some temporal task, mice end up doing these rather bizarre, stereotypical, almost basketball-like things because they believe that's part of what's required to succeed, where it isn't really required. So I wonder how much you get into a thing where you get these things and you learn spurious correlations. I don't know the answer to it, though. Okay, so I'm going to present a model. I haven't presented this so many times, so please stop me if anything's not clear. This model was really generated by a very talented PhD and now postdoc James Heald in my group and his collaborator Mattia Lengel. And the model's called contextual inference. We call it that because it's all about contextual inference, and the coin nature gives you the probabilistic nature. So I'm going to sort of take you through the generative model of how the brain may think the world is in a simplistic way. So the idea is that you're in one context at a time in this model. So here in the blue context, and over time you can transition to the blue context, then to the red context, then to the orange. So this could be different objects you're interacting with, or different environments, or different states of fatigue, whatever you want. But contexts change discretely over time. And the idea that each context can emit sensory cues. So for example, this context may be associated with some sensory cues, such as the visual appearance of an object. And this context may have different visual appearance of an object. So you can observe sensory cues which are informative about the context. And the contexts are then also associated with the state. So for example, the blue context may be associated with the state here, which might be the weight of that object. And that weight of the object could change with time, for example. So the state evolves. The red context associated with the red state and the orange with the orange state. Okay, so you can think of these, if you want a simple example, of different objects with different weights, and those weights can change. And then the idea is what you get to experience of the world is the sensory cue, which doesn't depend on your action, but something which does depend on your action, state feedback. And that depends on, for example, what the active context is in the state. So if the blue context is active, you experience the blue state. Here, when the red context is active, you don't experience the blue state, you experience the red state, and so on. Okay, so the idea is that context transition through time, you get to experience the state of your current context, sensory cues, and state feedback. And so the problem the brain has, if that's the way the world generates data, is to infer all the things the brain wants to care about. And I'm showing you those here. So the brain wants to estimate variables in this. And by variables, I think it means things which you expect to change with time. So for example, you expect the current context to change with time. And you want to estimate which context am I in? Am I in the blue context, the red context, the orange context, or so on? And given that, I'd want to estimate also what the current state of that context is, like what's the perturbation of that context or the weight of that object. So I want to estimate these things. There are also parameters you want to estimate, and I call them parameters because they're fixed in the model, but you as a learner will have to estimate them. For example, the number of contexts might be fixed, how context transition might be fixed, how the way contexts change with time, the way you emit these sensory cues you want to learn, and you want to know how states transition as a function of time. So I'm going to take you through some of the details. Now, these are sort of mathematical details. If you don't want to follow the maths, it's fine. I'll give you some intuition with some simulations in a moment. But those who want to understand how we actually parameterize for these things, they're somewhat important. So the idea is that contexts can transition a Markovian way, which means the probability of going from any context to any other context is governed by a single number, that probability. And so we can basically show a context transition matrix. So here I'm just showing you 20 contexts to another 20 contexts, and the color shows you the probability. So the way you would use this is if you're in context 1, these colors along here will tell you the probability of moving in the next time step to the other 20 contexts or remaining where I already am. And so the way we parameterize this with something called a sticky hierarchical Dirichlet process prior. It's sticky because you tend to stay in the same context, and that's why you can see this sort of diagonal is quite bright. So if you're in context 7, you tend to stay in context 7, although you might change. And the reason we use Dirichlet is it's a nice non-parametric prior, which means we can have infinite numbers of context possible, and it's hierarchical, such that effectively these rows are correlated. So a common context is one you'll transition to from any other context. Okay, so we've got 3 parameters which give us a prior over the context. And similarly, we can use a similar type of prior over the Q emission. So this is, given a particular context, how probable it is I'll get a particular Q, such as vision of a sugar bowl or vision of a cup. And that's governed by this matrix here. And again, it has 2 parameters. So this basically tells me the prior on how I believe context is going to transition and how sensory Q is going to be generated from context. These are my priors, but when I get experience, I'm going to update my belief on these to generate posteriors over these things.
Can you just say what these parameters are?
What the parameters are?
Yeah.
Okay, so in this case, one parameter is the stickiness. It's basically the parameter, one parameter governs how sticky I am. The 2 parameters are a bit tricky to explain. One tells me overall how the number of contexts are going to grow with time. Am I going to have a large number of infrequently experienced contexts, or I'm going to have a small number of very probable contexts? So that's one of the parameters. And then the 3rd parameter tells me basically how predictable the context transition will be, how similar they will be across different contexts. So there are 3 parameters to guide that. Oops, sorry, and that's similar for this. It basically tells me effectively how many Qs I expect to experience as time goes on, and the other one tells me how predictable a context will be for a Q. Okay. So that's the priors for the context transition emissions, and then we have to have priors for how we think states will evolve. And effectively, we have a very simple linear system which says, I believe my state is going to decay, so I have a retention parameter and it decays each time step. It can also drift and it can have noise. And I put simple priors on that. So we have a prior on the retention and a prior on the drift, just normal distributions. And then what I get to experience is effectively the state of the active context plus noise. So all in all, we have a number of free parameters we're going to fit to data. If we have an experiment which doesn't have sensory cues, we have 7 parameters to fit. If we are with cues, we have 8. And so we're going to fit those parameters to try and explain data. Okay, but let me give you an intuition for actually how the model works. So here is experience. So here is what you would experience. This is a state feedback, which you can think of as a sensed weight. So there are 2 cups. There are 2 sensory cues. Here's sensory cue, which you experience throughout this period, which is the vision of this cup. And this is what you experience as sensory cue, the sugar bowl. And as you handle a bunch of cups, you handle cup 1, which is light, then you go to cup 2, which is heavier, back to cup 1, to cup 3, which is even heavier. Maybe you empty cup 3 and back to cup 1, and then you go to the sugar bowl, which weighs the same as cup 2. Okay. Now, although I've labeled these things cup 1, cup 2, cup 3, that's what's happening in the real world. From your point of view, you don't get to experience anything about cups. All you get is sensory feedback, which is a noisy version of this. So you get the purple input, and you get a discrete knowledge of Q1 and Q2. And so we can run the coin algorithm on this to do inference given a set of parameters. And the first thing the model does at each point in time, it says, how probable is it this is a context I've never seen before? So it estimates effectively the novel context probability. So when it starts off, since it's seen no context, it says, oh, this is very novel. And so it's going to generate a memory for this cup 1. Turns out when it comes to cup 3, again, the novel probability gets very high, and so it generates another memory for cup 3. And when it comes to the sugar bowl, even though the sugar bowl weighs the same as cup 2, because it's got a different sensory cue, it's novel enough to generate a new memory. Note when it goes to this cup 2, although the probability goes up, it's not enough to generate a new memory. So the idea is that new memories are created when the novel context probability is high enough. And this is in a fully Bayesian way we're estimating this given the generative model. So effectively, by the end of this experiment, the subjects will have generated 3 different memories. And we can see what's inside those memories, because as it generates them, it represents the state of these memories. So we can see it starts off with a blue one. And what I'm showing you here is the estimated state for each context. So this is actually a full posterior distribution. So it starts off with an estimate of cup 1. Because when it goes to cup 2, it doesn't generate a new context, it adapts the state of cup 1 to cup 2, and up it goes, and back to cup 1. But when it goes to cup 3 in this case, because it generates a new context, we can see a splitting. Now we have a state for context 2 and a state for context 1. And similarly, when we go to the sugar bowl, we generate a third one. So this basically shows what the system is generating new memories over a function of time. You probably can see a gray background here. The gray background is the prior for novel contexts, effectively. Okay, so then it generates these memories, but we have to decide how much we should be using each of these memories at any point in time. And the way that works is the model also estimates the probability it's in each of the possible contexts. So to start off with, it's sure it's in context 1 because that's all it's experienced. But as it generates a new context here for the red, it starts to increase its belief that it's in context 2 and reduce its belief it's in context 1 and so on. Okay, and so estimating the context you're in and the state of the context, the natural and Bayesian thing to do is to combine these states with these probabilities to effectively express them. So you're going to express each memory related to your belief that that memory is active. So effectively, we multiply the blue by this blue line here, the red by the red line, and the orange by the orange, sum them, and that's shown here in the purple. And what I'm showing you then is the mean of that purple at each point in time by the cyan, which shows you the motor output. So the idea is you generate new memories, you track the state of those memories, you combine those memories based on your belief about each context being active, and that gives you this blue line here. And there's an interesting feature already. So for example, you can see that as you handle the heavy cup, you slowly seem to adapt to this. And often people think of this as like, you're slowly updating your state belief about it. But actually in this case, your belief about the state updates really rapidly for this parameter setting. What's slow in this case is your belief that you're in that context updates slowly. So it's a rather different view of motor learning, which says actually, you know the force you should produce, but you're just not expressing it because you're not sure you're going to stay in that context. And finally, we have to update the memories. And the way that works is after the movement, you can estimate what's called the responsibility. How responsible is each context for that movement? That's shown here. So when we believe that the red context is responsible, then we update it very fast. You can see it tracks the state very quickly. However, when we decide the red context is not active, we can see it sort of diffuses out as we become less and less certain. So the critical thing about the coin model, it does three things in a beautiful sort of Bayesian and consistent way. It tells you when to generate new memories, how to express the memories, and how to update those memories. Any questions before I go on to some data? Okay, so a nice test of the model revisits a paradigm developed by Maurice Smith in 2006 called spontaneous recovery. So spontaneous recovery is an interesting phenomenon, which is observed in the following paradigm. You bring subjects in, you put them in P0 for a while to get them used to the apparatus. You then give them some training in P+ to learn it. This is just showing the paradigm. You then give them brief exposure to the opposite, P-, with the aim of bringing them back to baseline. And then you put them in a long series of channel trials to sort of measure adaptation over time. And if you do that, this is the data you see. This is just showing you occasional channel trials. So they start to adapt in P+. There are no channel trials in P-, we don't see them, but by the end of P-, they've basically de-adapted. So when we go into the channel trial phase, you might expect them just to drift back to 0, but what you see is they tend to re-express some of P+ before decaying away. So this is called spontaneous recovery. It's a spontaneous and transient re-expression of this P+, having de-adapted them. Okay, and the way Maurice Smith and others have explained this data is what's called the dual rate model. The dual rate model is able to explain this, and this is showing you the output of the dual rate model. So the dual rate model learns, it de-adapts, but then it re-expresses the P+ in these channel trials. And the reason for that is that the dual rate model basically says there are two learners competing to learn. There's a fast learner and a slow learner. The fast learner, shown here in green, learns quickly but decays away quickly. Whereas the slow learner in red learns slowly but doesn't decay away so slowly. So initial learning is done by the fast, the slow learner takes over. And by the end of learning, most of the learning is done by the slow. So the blue is the sum of the green and the red. When you de-adapt, the fast learner de-adapts very quickly. And so by the end of the de-adaptation phase, although the net learning is 0, the slow learner is positive and the fast learner is equally negative. When you go into the channel trial phase, because there's nothing to learn, you just decay away. And because the fast learner decays away quickly, you get to re-expression of the slow learner effectively because it decays away slowly. Okay, so the dual rate model explains this with sort of two states which compete to learn. So we can compare that with the coin model run on the spontaneous recovery paradigm. So here's the spontaneous recovery paradigm. In our case, we give it a noisy version of this, and we can see what happens. What happens is initially, it's got one context. When it goes to P+, it spawns a second context, which tracks the P+. And when it goes to P-, it generates a third context. And so by the end of the P- phase, it's got 3 contexts. Once you're in PC, each of them basically decays towards 0. But critically, this shows you the predicted probability, the way that these contexts will be mixed to motor output. Initially, it's P+, mostly, initially it's P0, then as you're in P+, you become more confident. And in this phase, effectively, there's a slow decay. So effectively, because you've been mostly in P+, in the absence of any evidence, you tend to believe you're in P+ again, because it's the most common context you've experienced so far. And so if you apply this, what you see is a nice spontaneous recovery. But this is quite different. So in the coin model, we get changes in motor output independent of changes in internal state. So you can get rapid changes due to your belief that a context has come back. In contrast, in the dual rate model, the dynamics of the motor output is solely determined by learning. The only way you can change it is by learning. There's no concept of a time varying expression of different states. And so although both the coin and the dual rate model can explain this data, we can change this paradigm just very slightly to show a very strong difference in the predictions of the two models. And the way we do that is we change this by just 2 trials. So having gone through P0, P+, P-, 2 very early trials here, we give 2 P+ trials. And the reason for that, that gives very strong evidence to the coin model that P+ context has come back. Whereas for the dual rate model, it just gives 2 learning trials, which doesn't really adapt you very much. And so what we see in this case, rather than the slow increase in the context for the P+, we see a very rapid increase. And rather than seeing the spontaneous recovery, we now see what we call evoked recovery, a very rapid increase to a high level, followed by decay. Okay. And so we can run 2 groups of subjects. Here's subjects run on spontaneous recovery. We see this nice thing here. Here's a group run on evoked recovery where they have just 2 P+ trials here. And we can see they get a very high level, followed by decay. If we look at the dual rate model, it can do a good job here, but it really misses very badly here. The dual rate model can't capture both the increase and the slow decay, whereas the coin model does a pretty good job of this. So the coin model suggests both at a group level and a big level, very strong support for this, suggesting that perhaps what's going on in these sorts of paradigms is not just states just tracking this or multiple states, it's actually generation of new memories and estimation of probabilities. So context estimation, we think, controls memory creation and expression in these sorts of paradigms. So I've talked really about memory creation and expression, but we want to also show that memory updating is also controlled in the same way by these sorts of paradigms. And so in a state space model such as the dual rate model, the key idea is, you've got some states you want to estimate on this trial. It's the state of the previous trial plus some error times some gain. So basically you make some error, you want to update your belief about the state, you didn't generate enough force, and the amount by which you should update it is usually governed by the Kalman gain, which tells you how much to update it. And that's very straightforward. But when you go to models such as the coin, life becomes a bit more complicated in that you've got multiple contexts and you might want to update multiple contexts on any trial. And the right thing to do now is to update the jth context state by again the Kalman gate and error, but now by how responsible you think that context is. So this thing tells you my belief that that context was active on that trial. Okay, and this responsibility is governed by 2 things. It's governed by the sensory cues you experienced and your state feedback. And so what we really want to ask the question is, can we find evidence the amount you update your state is governed in the way the coin would predict based on the responsibility here? And the way we're going to do that is we're going to try and manipulate this responsibility on different trials and ask how much learning you get on a single trial. And so the way we're going to do that is the responsibility, as I said, is governed by two things. It's governed by sensory cues. So we're going to have two different sensory cues, 1 and 2, and they're actually going to be the control points in that object. And then it's also governed by the state feedback you get, which is the perturbation, so P plus and P minus. And so the way we do that is we're going to train you like we did in the control point on P plus with Q1 and P minus with Q2. So we leave you lots of experience of those. And so the idea is that hopefully you're going to learn there's a context which emits Q1 and gives you P plus, and another context which gives you Q2 and P minus. And so hopefully you're going to learn that the blue context is associated with Q1 and context and plus, and P2 and minus is the other. And then the way we're going to assess learning is with what we call triplets. We're going to give you, sorry, the transitions are driving me mad, right? We're going to give you effectively a channel trial with 1 Q, P1, followed by something, and then another channel trial with P1. So we're going to ask how much do you change your learning between the first and third trial, which is basically associated with one of the Qs. So with this context here, we're going to assess when we give you 4 possible single trials in between. And we can give you a trial which you've seen before, P1 plus or P2 minus, or we can give you a trial which is now novel to you. We can associate Q2 with the plus force field or Q1 with the minus force field. And so what this basically is going to tell us is how much you update your context for this state based on one of these. Okay. And that's what I'm showing you here is single trial learning. How much after you've experienced lots of this training do you update between these 2 channel trials based on the single trial? And the answer is you update the most for the P1 plus and the least for the P2 minus, intermediate for the others. And I want to try and convince you this makes sense, because as I've said, the responsibility which this should reflect depends on 2 things, the prior. And in this case, before you move, once you've seen this Q on this trial, for example, if you see the 1 Q, you should have a high prior belief you're in context 1. If you see the 2 Q, you should have low probability. So that shows you the prior based on the Q. Having experienced the force field, if you experience the plus force field, you should have a high likelihood for context 1 and the negative force field low likelihood. So as a good Bayesian, you should multiply the prior by the likelihood, which gives you this and gives you just the sort of updates we see, suggesting that the way you update multiple memories is by combining knowledge about the Qs and likelihoods in the way the coin model will predict, and we see very beautiful updating. And just to convince you, before any learning, there's nothing special about the Q or the force fields. Everything's updated the same as the model would predict. The model isn't just predicting these end stages, the model predicts the entire trajectory of learning. That's really important. So when we fit the data, we're fitting it to the entire series. Okay, I'm just going to finish in the last couple of minutes by saying, we can take now the participants we run those previous, we individually fit those subjects to the coin model. There were 40 subjects in total in the previous experiments. We can take those 40 parameters now and make parameter-free predictions on other paradigms. So we can say what would happen to those 40 subjects were they to run on this particular paradigm. And so here's a savings paradigm. In savings, you learn something once, P plus, in this case, it's a spontaneous recovery, you wash it out, and you come and learn it again. And what you see is the second time you learn it, you're faster. That's typical savings. When you've learned something once, you go away, come back, experience again, you learn it faster. And people have suggested the reason you might do this is you might increase your learning rate, for example, the second time around. If we run the coin model on this data, the model reproduces this behavior. So if we run the model just on this paradigm, no fitting at all, it's just the 40 participants parameters, we see this. But what we see is the Kalman gain, which is actually the learning rate, is the same both times. The state inside is also the same both times. What's critically different between the first and the second experience is your belief that you're actually in the new context, okay, for this perturbation. And the reason for that is that P plus is expected with higher probability the second time having experienced the first time, your belief that this context exists in the world has increased. So effectively, we think contextual inference is a critical thing which drives savings. Cut a long story short, the same thing is true of antegrade interference. Antegrade interference is something which says the longer you learn P plus for, the harder it is going to be to learn P minus after. And that's shown here. If you learn P plus and then get a P minus, you're slower to learn here than you are to learn here. And that's just shown in these little insets. And again, the model reproduces this very nicely. And again, it's nothing to do with learning rates or state. It's got to do with the fact that the more experience of P plus makes you think that it's going to be less likely that it will move to P minus. So it's all about contextual inference driving these sorts of effects. And similarly, this is from a science paper suggesting that learning rates, was claimed, depends on the environmental consistency. So if you're in an environment which switches between P plus and P minus rather rarely, you should increase your learning rate because the environment is going to be rather stationary. On the other hand, if you're in an environment which switches a lot, you should decrease your learning rate. And so they did these experiments, measured effectively the learning rate in single trials. The learning rate went up for the consistent environment, down for the inconsistent. If we run our model on this, we get a qualitatively similar effect. But again, it's got nothing to do with learning rates. The learning rates don't change at all. The critical thing is how much I believe I'm going to be in the same context next trial. So if, for example, I'm in a consistent environment, I believe I'm going to be in it, therefore I express more of what I learned. So it's got to do again with contextual inference and nothing to do with learning rates. Okay, I'm going to skip the cognitive thing and just move to the end. So we think we're beginning to understand some of the rules for motor memories and sensory learning in terms of leading and follow through, but we're excited about the coin model because effectively it suggests, rather surprisingly, that contextual inference is a key thing which dominates many of the properties of motor learning. It's not about learning state, which may be fast, it's about estimating the context you're in. It's a principal Bayesian model, and it's comprehensive in the sense that at the moment it uses all the cues available to the brain. I mean, maybe in a rather simple model in terms of sensory cues and state feedback. And it's also unifying in that at the moment, all those different models, all those different paradigms require different models to explain the behavior. So it unifies disparate data sets. And we think that sort of basic principles of this, of like taking continuous sensory motor experience and breaking it down into pieces, could be relevant to all forms of learning in the motor system and beyond. And obviously I want to thank my collaborators and particularly James, who did really the bulk of this work. Thank you. Happy to take any questions.
I want to ask, earlier you said something about explain why the adaptation doesn't reach 100%, and how does the coin model explain that?
So the coin model, we haven't really thought about that in a lot of detail, but the coin model always assumes decay. And so if you assume there's decay, which is a parameter in the state transition, then you'll reach some asymptote effectively, which you will decay to. So you'll never reach 100% because of that, if you believe your prior is that things tend to decay. That's the way we account for it. We also account for like long-term learning by the drift parameter. So learning the drift means that at some point the drift going up and the decay going down reaches an asymptote. So you don't actually come back to zero ever. So when you don't observe a perturbation for a long time, it doesn't go away fully. It maintains that memory. That's the way we have long-term memory in this model to some extent.
I know you skipped the cognitive bit.
I did. I ran out of time. Yes.
Yeah. But I do wonder how it's related to cognition. I mean, we're talking about beliefs, but I guess you don't really, this is done probably implicit. Oh, yeah, there you go.
You want to know? I mean, it'll take too long to go through. I mean,
okay.
So, okay, I can tell you very briefly. So, you know, people, I will do a brief version for you. Now I know I've pronounced your name wrong all these years. You never told me. I found that out today. Okay, anyway. Okay, so people have looked at the issue in visual motor learning of explicit and implicit learning. So if you learn a visual motor rotation, this is total learning, but you can break it down to an explicit component where subjects say they're going to aim, shown by this dark green, and therefore the remainder is implicit. And they have these rather interesting time courses of what you're aware of and what you're not aware of. Okay, and so people have tried to associate this with the fast and slow learning of the dual rate model. The way we account for this is that effectively we have to change the paradigm from the dynamics, because in this case, effectively there's a sensory bias. So now what you experience of where your hand is and where your hand really is can have a bias, which is a proprioceptive visual discrepancy. And the idea again now, you've got a problem of deciding when I get a perturbation, is there a perturbation or am I just miscalibrated in terms of where I think my hand is? And so in our model now, we assume that you have explicit access about the rotation you estimate, but only implicitly you don't know what your sensory bias is. So when I go around the world, I'm not aware of my sensory biases. I've calibrated them. And if we run that model using our coin, I'm not going to take you through it because it'll take long, but the paper's online so you can read it in detail. We can explain that behavior in terms of the bias. So effectively, this is the bias, and this is the sort of rotation learning. So that's how we explain it. So we're suggesting that effectively it's got nothing to do with fast and slow learn. It's got to do with you're learning a bias, you're learning the rotation, they sum up together, and the bias you're just not aware of. And it'd be weird if you were knowledgeable about your bias. I mean, when I see my hand, I believe it's where I see it. I'm not aware of a bias, and if you put me under vision motor rotation for long enough, I calibrate for most of that bias. I'm not aware of it. So that's a way we're beginning to explain it. We've also got some other work on working memory. So we think working memory might be required to maintain your context probabilities. And so if you basically have to working memory task, you lose those contexts and it resets them in some way.
That's exactly, that was my second question. How is it related to cognitive processes? And
we've done some modeling work on that. So if you want, the paper is have I just stopped sharing my window? Am I sharing still?
No.
Okay. So the paper's available here. So we've looked at cognitive tasks as well. So the idea that a working memory task might reset this. So we're trying to map on different elements of the task to what's explicit, implicit, and what you're aware of. In fact, we do make a quite strong claim in that that you're not aware of the state of all your contexts, but only the most probable one. So we can only explain that data, explicit and implicit, if we assume that you only can report your most probable context. You can't report the average of all contexts, which is sort of interesting and is in alignment with some of the work done by Simon Chelly, where they show that explicit reporting bias is what you're going to do. Yeah. So any other, and we've also compared it to many other models, but I won't.
I want to ask also, I know there's a lot of therapists in the audience here today from different fields. So I don't know if you have any sort of practical predictions you can make based on this model for if people have to learn.
Sure. So we've been thinking about that. So basically, one of the problems with my understanding, I'm not a therapist, but one of the understandings when I talk to them is that, you train someone in the lab to do something on a treadmill or with a robot, and then they leave and it doesn't generalize outside the lab. So it doesn't generalize. And so, that's a very clear context-specific learning where you've got some context which might have sensory cues or state feedback which don't map onto the outside world. So although they might have generated this wonderful learning thing which they can express in the lab, they can't do it outside the world. So one critical thing would be to make sure that you can blur the edges, somehow to provide sensory cues or confusion to make it hard for them to distinguish the outside world from the laboratory world. So we've been thinking about situations where you would want to, for example, you would want to bring in perturbations slowly in the lab so they don't generate a new model, but they adapt to an existing model, or to make the environment confusing in some sense, so you can't be sure whether you're in the lab or the real world. I haven't thought how to do it, but you need to basically allow them to access the same things outside the lab. So we've been thinking about that. We have a grant now to study this with the aim at the end of it, trying to get to the idea of how you could manipulate context effectively so that you can either make it more distinct, but often less distinct is probably what you want. Does that make sense? Okay.
Okay. Are there any other questions?
I have one question, if it's okay. Can you explain what you were talking about in the beginning with the follow-up? How does that work with the coin model that you need a prior?
Okay, so I'll be honest, it doesn't totally fall into this, the follow-up. I think it might be a different mechanism. The way you could imagine it following in, if you believe, for example, that moving in from the left is one context, moving straight ahead is another context, then if you learn very strong priors, context transitions, that this leads to something else, that might allow you to access those different contexts. But my guess is probably that's not the way you're doing it. My guess is it's a lower level thing about chunking of what a movement is. Okay, so I think the point is that two separate movements effectively have different neural activity than one continuous movement with a follow through. And I think that makes it a different sort of movement allows you to associate it with a different a different set of dynamics. So it doesn't fall totally into the coin framework. Well spotted. Thanks.
Okay, thank you.
Great. Well, I'm delighted you're going to have a motor learning hub. It's exciting. It's always good to have more people doing motor learning. So I will leave you, though, to have your planning meeting. Okay.
Okay, great. Thank you very much.
Thanks so much. Okay.